Hi, in this video we're going to finish our discussion of section 13.1, which is going to involve sketching space curves. So in the last video we talked about some of the algebra, even some of the calculus like limits of space curves. I think that stuff's pretty easy. Sketching can be pretty hard, especially when you're a bad artist like me. Look forward to a GeoGebra video where we'll look at some of these curves more in depth. And a lot of times GeoGebra would really be necessary here because it's kind of arbitrary. It's kind of hard to think about what surface these would even live on. So it might be hard to draw these. It might be impossible to draw these. It certainly will be for me. But there are a few where we can at least get an idea of what's going on. So just like in the last video, I want to recall what the situation was in 2D. In 2D, what we're looking at is a parametric equation set up where we have x of t equal root t and y of t equals something like 4 minus t, right? I want to note these can be translated into a 2D vector valued function, and we'll see these a lot. These will actually be easier for us to graph and such because we know how this goes in 2D. You could do all of what we did in chapter 10 of Stewart or in your parametric equations unit by talking about these 2D vector valued functions. If I wanted to sketch this, what would I do? I would start to think about, well, if x equals root t and y equals 4 minus t, we often figured out we could get a path here by solving for t, x squared, with some domain restrictions, right? Like t had to be positive here, careful. And therefore, y would have to equal 4 minus x squared. And we would have thought, okay, well, what sort of function is that? What sort of function is that? What sort of function is 4 minus x squared? It's a parabola that opens down with certain intercepts. This is probably not to scale. It's a pretty good parabola for a dashed line. And we have to assess, okay, well, what's going on here? Well, t had to be greater than or equal to 0. The intersection of those two domains, again, right? The domain for x and the domain for y. And if we find out where t equals 0, we have r of 0 would be the coordinate 0, 4, or the vector 0, 4, which is right here. And then as t progresses through time, you should be able to reason through this, but the real method we will use a lot of the times is what's r of 1? What's 1 second later, where are we at? And we can just try to track it. They'll be really useful in 3D. Oh, it's 1, 3, so that's here. So we're talking about this half of the parabola with that orientation, with us proceeding down. And that's a space curve, except it's only living on that 2D plane. And so we can go further by taking this into 3D. So here's my rules. Steps. Identify x, y, and z for 3D. Use one or more components to get a curve or surface. And just like with 2D, we eliminated the parameter. That's what this is called, eliminating the parameter, and that told us what curve we'll live on. Remove t or eliminate. And it doesn't have to just be x and y. For two components x and y, sorry, which is what we did all in chapter 10, parametrics, x and z, that kind of idea, y and z. You're missing one of the letters. Your sketch is on a plane. Like when we just had x and y, our sketch was on the xy plane. So if I just have y and z, my sketch will be on the xz plane. Sorry, if I just have x and z, my sketch is on the xz plane. I don't know if I said that right. For 3 components, the curve, or the sketch, I guess I was just calling it the sketch, is on a surface. And then 3, use values of t to get orientation. And that's what we were doing at the end. T equals 0 and 1 are really good options unless they're not in the domain. Hopefully that's clear. So we're going to start with something that should look very familiar. It's going to be presented slightly differently, but it really should look familiar once you get used to seeing this kind of guy. We have 1 plus t in the I direction, 2 minus t in the j direction, and 3 minus 2t in the k direction. What would the sketch of this guy look like? So here we go. We write down our x is 1 plus t. Our y is 2 minus t. Our z is 3 minus 2t. One thing to notice is that the domain of all 3 of these functions would be all reals. So the domain of R is all reals also. And these should look familiar because these are the parametric equations of a line, right? We have three variables, all with t, all linear. That's parametric equations of a line. So it's going to be a line in 3D space. You need to learn to recognize that. We can get t equals 0 to get 1, 2, 3. T equals 1 produces the coordinate 2, 1, 1. And we can try to draw it in 3D space. Now, why wasn't I talking about a surface? Why didn't we have to eliminate perimeter? Because this is our standard function. I think that looks straight, but I don't know. Sorry. So 2, 1, 1. Just trying to get some coordinates. 1, 2, 3. And then we're going to offset like that way. Like that'll be my initial point. And then 2, 1, 1 will be somewhere over here. So what we're dealing with is a line going through both of these, ideally, with a heading that way. Because this was t equals 1 and this was t equals 0. So it's flying through 3D space. I know it may not quite look like that, but you should be able to visualize a line at this point. It's a 3D line. It's just a laser beam going through space in one direction. So let's look at a more complicated example. This is actually a pretty famous example. R of t equals t in the first component, t squared, t cubed. We just think that's really interesting, right? You go up a level each time, up an exponent each time, and we'll give you a domain here of t greater than 0. So this is called the twisted cubic. And we'll talk about why. Why is this the twisted cubic? So we're going to start by labeling our x, our y, our z. This should be really easy for you right now. T, t squared, t cubed. We're going to look for a place to eliminate variables. Since we already have x equal to t, it means that anywhere I see t, I could replace x. Not that revolutionary an idea, I hope. So just like in parametric equations, if x equals t and y equals t squared, then y equals x squared. Pause and think about, what if we did these two? Would that also work? Yes, that would work just fine, but we do have a better idea of what this looks like. If I graph this guy in 3D, you should think back to 12.6 and consider what this looks like. This blue function, is it a more general surface, like a quadric surface, or is it a cylinder? This is a cylinder. Why? Because it doesn't have all three variables. What kind of cylinder? It's parabolic. The traces are on the XY plane, directed along the Z axis, the missing variable, yeah? So, this is a surface we're familiar with. This is what I mean when I say that direction. We want to get a surface we're familiar with as opposed to something like x equal or y z equals x cubed. It might be harder to draw. I'm going to try to draw the cylinder. Do my best to draw it. There's one trace when z equals 0. And if we go up higher, I'm just going to go to the top of the z-axis so you can really see the sheet. We'd have, just trying to keep everything parallel. Like, that's the surface this curve lives on. A parabolic cylinder, okay? That's not the curve. That's not the space curve we have. That's going to be the surface that the curve travels along. And then what we're going to do is the unused component, back to Boulder. So the unused component, unused. I'm spelling it right. Component is what the curve looks like on the surface. Now, what the heck does that mean? What that means is what we're going to do is, like, okay, basically y equals x squared gives me the surface, and z equals t cubed, it should look like the cubic function. Except I'm not graphing it on like the xy plane. I'm graphing it like the surface I'm looking at right here is my xy plane. So when t equals 0, we have the point 0, 0, 0. That's why I just did that in red. And when t equals 1, we're going to have the point 1, 1, 1. Not that interesting. But when t equals 2, 2, 4, 8. So we're going to try to graph each of these points, and it's okay if you can't quite visualize it. But 1, 1, 1, I think should be about here. So we're picturing that above the x-axis, above. And then we're going to hit 2, 4, 8. So a little bit further out along the x. much further out along the y, and then at the peak of the z, really. So we're talking about probably something along the lines of here. And so what we're having is something that's traveling along the surface and then skyrocketing up. And so I know that's not the best picture in the world, but that's what you got. So it's very hard to see. It's twisting around along the parabolic cylinder and then shooting up. I'm going to try to draw a different angle of that picture. Maybe that'll help. So my cylinder is going to be in blue again. The trace along the XY plane. The trace at the peak. Here, we'll try to actually do it justice now. So 1, 1, 1. Be here-ish. Not the easiest to draw. And then 2, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. So if I try to draw this point, that'll be my third point along the curve. So here's the other piece of my cylinder. So this is the sheet we're traveling along. It goes on forever. Again, don't picture that as a closing off point. And my cubic is twisting along this way, traveling along the surface in that fashion. I think that might be a better visual to look at. And again, we'll maybe play with it in the GeoGebra. Tempting fate, let's try another one. What if we looked at r of t equals 2 cosine t I hat plus 4 sine t j hat plus 3 k hat. X equals 2 cos t, y equals 4 sine t, z is just stuck at 3. It's going to be very helpful for us to look at. Again, we're going to try to eliminate the parameter. Do you remember how to try to eliminate the parameter when we have a cosine and a sine, right? This looks like, well, x over 2 equals cosine, y over 4 equals sine. And so what we have here is x over 2 squared plus y over 4 squared equals 1. Again, this should be clear that this is a cylinder. Why? It's a ellipse directed along z. It traces parallel to xy plane. The z is the missing variable here. So what we're going to have here is a cylinder. And in this case, we do mean the traditional kind of cylinder, not like a parabolic cylinder, but a real straight up cylinder. And what's it going to do? It's going to just float at a specific spot. That's what the z is doing in this case. So if I try to draw my xy z axis, we're talking about a cylinder, and it's a little longer in the x direction, sorry, the y direction. So that's our cylinder. And then what is z equals 3 doing? Z equals 3, one way to think about this is on the cylinder. Find that on the cylinder. Well, what's that saying? It's saying go up to a height of around 3, and we're going to take all of the points that have z equals 3 on that cylinder. And what that looks like is basically one of these floating traces. And that's what we would have here. We would have like a floating ellipse in 3 space. How do I know that's the orientation? Because when we have cosine and sine, when x is cosine and y is sine, this is the standard orientation in the counterclockwise direction. Why is it floating at a height of 3, at a z coordinate of 3? Because that's what was given to us in the equations. If it helps you, you could graph some points. T equals 0. What do you got? You got 2, 0, 3. T equals, you don't want to use 1 for trig. We want to use something like pi over 2. You'd have 0, 4, 3. So we're talking about this point at 0, this point at pi over 2, and that's how we're going to get this orientation. I hope that's clear. So again, it's not the cylinder, it's the path on the cylinder. So it's like a bug walking along the circle, walking along the cylinder in that horizontal style direction. Again, horizontal depends on the orientation here. But if we're like facing the z-axis, it's walking parallel to our eye level, so to speak. Okay? Let's see how changing a few things in these styles of equations would change the outcome. So what happens if I do something like cosine t? Sorry. Let's do r of t. Cosine t I hat plus sine t j hat plus t k hat. So now we gave t a direction. Sorry, now we gave z, z gets a change too, right? So one more time, we'd still have x equals cosine t, y equals sine t, z equals t. So in this case, we'd have x squared plus y squared equals 1. That is our normal, I almost want to say stereotypical cylinder along the projected along the z-axis. Projected along the z-axis. So now it is our unit circle. Let's go back to thin lines for the projection. It's our unit circle projected up along the z-axis. So what's z equals t going to do? Z equals t, right? As we rotate along that unit circle, t wants to increase our position. So we might do something like t equals 0, and you would get what? Like try out a few points. See what's happening. Try t equals 0, try t equals pi over 2, try t equals pi. What happens? Here I go. 3, 2, 1. T equals 0, we have 1, 0, 0. Pi over 2, we have 0, 1, pi over 2. Pi, we have negative 1, 0, pi. So what's happening? we're still rotating around, but by the time we get to pi, which is this sketch here, we're at pi over 2. Sorry, by the time we get to pi over 2, you're going to draw that a little smaller, we're up there. Our z is increased, and by the time we get to pi itself, we're going to go up even further. So trying to sketch a line like z equals t, just a nice linear growth cycle, is actually wrapping me around that cylinder. And so what we're doing is we're tracing a helix shape, which is like a fancy word for a spiral, as we go up and up and up along that cylinder. We're going to try to draw a few more things. We're going to make one more big change here. Now let's do x equals t cosine, y equals t sine, and z equals t. I guess I didn't label this as a vector valued function, but I hope you see it by now. That when we have a parameterization with 3 variables, we're creating a space curve. So we can start by combining these two. X over t would be cosine, y over t would be sine. And so then x over t quantity squared plus y over t quantity squared would be 1. And I'll show you one more technique here. So in general, you could solve this as x squared plus y squared would equal t squared. So we see that we don't really have a surface, right? But then we can remember that z equals t. And so we would have x squared plus y squared equals z squared. What surface does that create? Do we have 2 variables or do we have 3 variables? We have 3 variables. So we're talking about a quadric surface. And do we have constants? It's those questions again. Are they all squared? You might remember that this is a cone. Ideally, you remember that this is a cone. And so we have, I guess I changed my color scheme, is a cone. And then what's going on this cone? Let's find some points to trace out my curve. I guess, no, I'm going to change the colors. It's going to really bother me and maybe you too that we have, that was such a good cone too, that we have a cone floating in 3D space. I'm going to recast this as blue. I'm so sorry. Tragedy. And when we try to look at my curve here, t equals 0, t equals, again, trig, so we're talking about pi over 2. What are we getting? 0 is going to be 0, 0, 0, which makes sense because my cone touches the origin. How about pi over 2? Where are we at? Pi over 2 is actually going to give us something like 0 on the x still. Pi over 2 for the y coordinate, and pi over 2 for the z coordinate. So that's maybe up here, if you can picture what I'm laying down. What about t equals pi? Got negative pi, 0, pi. It's back here. So what's happening? What's happening is as we spiral now, I'm getting farther and farther from, I guess that should all be dotted. I'm getting farther and farther from my origin. It's getting further and further out. So it's not just a sort of helix. It's traveling further and further from the pole, further and further from the center in space. Can you see that? Further and further distance from the origin itself in terms of the, I don't know, lateral distance. I'm going to show you what this looks like if we just focus our attention on the X and Y. If we just focus our attention on the X and Y, what this looks like is literally a spiral. So none of this actually exists on the XY axis, okay? What we're doing here is like trying to show you a level curve kind of idea, which will come up later in this course. And that's what's getting wrapped around the cone as we travel up along the z-axis. All right, I hope some of this made sense. We're definitely going to look at a GeoGebra video and see what things look like. Maybe we'll play around with some of these. Thanks for watching. I hope you learned something new, and have a nice day. See you next time.